Hi, welcome back. It's my pleasure to introduce the next invited speaker, Hugo Larochelle. He is a research scientist at Google Brain and a lead at Montreal Google Brain team. He is also a member of Joshua's Bengio's Mila and Adjunct Professor at Université de Montréal. He has made a number of contributions to the foundations of deep learning, including unsupervised pre-training of deep networks, denoising of the encoders, zero-shot learning, domain adversarial networks, and meta-learning for few-shot learning. He was program chair of ICLR 2015, 2016, and 2017, program chair for NeurIPS 2018 and 19, and general chair for NeurIPS 2020. He is a member of the boards of NeurIPS and ICML, and was founding member of the board of ICLR. Presently, he co-founded the Transactions of Machine Learning Research.
All right, thanks for the introduction. Thanks for inviting me here. Good morning, everyone. So this is my first in-person talk in forever, which I guess is probably true for a few people who'll be presenting. So I might be rusty, so bear with me. But at the same time, I feel it's also one of the few opportunities we get to kind of talk to each other in person. And so I'm gonna try to keep this short and put in some opportunities for exchange and discuss. And hopefully even it could be during the talk. I don't mind if someone comes up to the mic and wants to ask a question. Or if you want to wait at the end, that's also fine, but please don't hesitate to interrupt me. And in many ways, the talk that I had in mind is kind of meant more to be brainstorming in nature, where I'm going to try to sort of put forth this framing of thinking about how we solve few-shot classification problems through the lens of something I call recycling deep learning, which is not a formal thing, but it's more like a point of view, which I think can be interesting to sort of use to think about all the work that we do and how we might want to move forward. So I will do that as soon as I figure out how to advance my slides. There you go. All right, so what I'll focus on and the type of task I have in mind for this full talk is illustrated here. We're going to think about few-shot image classification. That is, we're given a training set that's very small. In this case, it's the extreme case of one image per class, where we have 5 classes. And in few-shot classification, we're interested in methods that can give you, for this training set, a classifier that will generalize well to new examples on some test set, as in here. All right, so that's the kind of problem that we're hoping to solve. And we're going to do that through a form of transfer learning. And I think a lot of people, certainly in this room, but I think in general, actually in our field, more and more are very much interested in doing that. I think this has been a research agenda for me for a while, but I think for many others as well. We acknowledge that you're relying on a lot of labeled examples where every single task we'd like to solve with deep learning is not really reasonable. And also scientifically, it's kind of interesting because we know people also learn tasks, from small amount of examples or experience. And so there seems to be also a gap between the systems we've engineered and our own ability as humans to learn new tasks. And so there's something there also that's also interesting to study beyond the technology that would be beneficial if we could do few-shot learning effectively. And one of the most prevalent approach is what I've referred to here as the pre-train plus fine-tune approach. In fact, it's so prevalent that when people say transfer learning, oftentimes they actually mean this. They sort of equate transfer learning to pre-train plus fine-tune approach, which is a little bit of a pet peeve of mine. I think transfer learning is much broader than this, but pre-train and fine-tune is definitely like one of the most robust and popular way of doing transfer learning. And in that setting, how do we approach solving a downstream task that has few examples? Well, upstream, we sort of assume that we have a lot of data for some task, and then we're going to pre-train our model with, say, regular training. So oftentimes in image classification, that means just training on ImageNet, and we have a lot of images from ImageNet. So we train on that upstream task. The upstream task here would be ImageNet. And then we effectively recycle the weights that we produce from our pre-training, and we use that to initialize the model that will then fine-tune on the task that I will call the downstream task, that in few-shot learning has very few examples per class, if it's a classification task. And so I've introduced this term here. I've used this term recycling And we're going to sort of play with that, and we're going to encourage you to think about it in this way in this presentation. Because in a way, it is a form of recycling. We're taking something that was meant for something else, and we're going to reuse it, to repurpose it for a new purpose. Hopefully, sort of, taking advantage of the resources that went into creating the first artifact, which was the pre-training, so as to limit the amount of resources we need to deploy for the new purpose, which is our downstream few-shot class. And now, why is that potentially useful, to sort of play with that concept and think about things in this way? Well, I think one possibility where I think this is maybe interesting to sort of inform our point of view is that when we think about transfer learning, I think we're oftentimes mostly concerned about trying to not rely so much on a lot of labeled data downstream. And that's the resource that we're trying to save. We're trying to avoid requiring so many examples downstream. But in fact, there's, data is not the only expensive resource when we're trying to solve a downstream problem. Compute might also be a problem. Memory might also be a problem. And so by sort of using this term, this presentation, I'm trying to encourage us all to sort of think beyond that and think about generally what kind of resources come into when we're training these models, and trying to think about the ecosystems of models that we're training. How can we sort of be resource efficient, whether it's labels or data, compute, and memory, and so on. So I'm hoping that, by just, stating this term or using it, it increases our focus on when we do pre-training of wanting to create as much value for many different downstream tasks. I think that can sort of legitimize putting a lot of compute in pre-training if it turns out that in the end, it helps a lot of other tasks downstream. It also encourages a reduction of compute and memory for resources used downstream. So an example that will sort of come is that when we do pre-train and fine-tune, we need to effectively copy the weights and then fine-tune them. And so we need to instantiate a new copy of our classifier in the downstream task. There might be settings where that's not really reasonable, where we need to introduce a small number of weights because we have some memory constraints, perhaps in terms of storing all the weights for the different tasks that we want to solve. And so that's something to think about. And generally, I like the idea of us to think about transfer learning more in terms of like, we have a lot of different tasks that as sort of engineers of machine learning, we would like to solve with machine learning. And so let's try to think about how do we take the somewhat limited amount of resources we have to serve all of these different tasks that could be solved with deep learning. This is partly why we introduced recycling in our economy, is that we kind of felt like we had a lot of different purposes, or this material was useful for a lot of things in our society, but the amount of resources to produce all that material was somewhat limited. So we sort of thought about recycling to try to allow for all of these purposes while relying on less resources. So I think we can have this kind of mindset as well here. And this is kind of what I'm suggesting we maybe have in mind in this more kind of speculative presentation here. And it's kind of interesting because in a way, I think a lot of researchers already kind of rely on transfer learning for forms of, through sort of a motivation that's kind of related to recycling. People will download some weights from an ImageNet pre-trained model, partly I think sometimes because it speeds up, training that model in that downstream task because it's more or less already trained. I was kind of, but the word recycling had never been used before. But then recently I saw in DeepMind's Flamingo paper, which has been really, really interesting, in their sort of broader impact statement, they kind of mentioned that because they're reusing some frozen language models and visual encoders in their work, and they kind of talked about that as doing a form of recycling. So I thought maybe that term is not completely crazy. At least some people seem to think like intuitively, maybe it makes sense. And so really, I'm not necessarily strongly advocating we should do this, but I think it's kind of interesting in the context of a workshop to kind of think differently about things and see where that brings us. And so, but going back to pre-train and fine-tune, I sort of suggest, well, should we sort of expand the kind of tools that we have for doing transfer learning, because other approaches might be more beneficial from other reasons than, well, they allow us to generalize better from the same amount of small amounts of data downstream. And in many ways, I think there's probably a lot of people here who actually already know that it is fine-tuning is not always the right thing to do. It's not always the best thing to do. I'm just giving you this example, which is quite relevant because this is going to be presented at CVPR this year as an oral. This comes from my group, Cristina Vasconcelos, who's going to present that on Thursday. And this was in the context of taking a pre-trained ImageNet backbone and using that for object detection. And what they had shown, if you freeze the backbone, you actually reduce drastically the amount of compute that's required for solving that downstream task. And interestingly enough, also actually, it also brings oftentimes for different types of backbones an improvement in terms of performance, in terms of the quality of the solution that you reach. Okay, so clearly that suggests that there's more to pre-train and fine-tune. And in this particular case, it's even better motivated by the fact that it requires less compute to actually solve the downstream task. All right, so my goal really is not to go really deep into a very specific technical result. I kind of want to present a few research vignettes for us to kind of think about different directions that are sort of taking different approaches to pre-train and fine-tune as a way of recycling some pre-trained backbone. And so I'll try to go fairly quickly over these, but I'm happy to answer more specific questions later on. And so I categorize these into two different sort of categories of approaches. The first one I'll go through is to think about approaches where instead of trying to recycle the representation that's given to you at the end of the backbone, to actually think about some pre-trained backbone that's providing you with a set of representations, a multi-layered representation, and actually try to leverage the richness of that, as opposed to just assuming that the representation only lives at the top. And we'll see how that can be beneficial. And then the other one, which I think has not been looked at as much, is in a setting where there might be multiple pre-trained backbones that are available, multi-sources from which we can do some transfer learning, how do we combine that into a solution for a specific downstream task? And I'll talk about some of the ideas that we explored recently about that. Let's start with the first one on recycling different levels of representations. So if we're particularly interested in having a downstream solution that doesn't require a lot of memory or in terms of storing the solution and compute as well, linear probe is a really attractive approach. If presumably you know what linear probe is, or maybe you know it through some other name, but essentially what it corresponds to is you just take your pre-trained backbone, you don't change it, you freeze it, and you only train a head on top for your downstream classification task. After perhaps having trained so the pre-training, I'll assume, has been done on ImageNet, and then we have some downstream tasks, and we have a bunch here that are listed at the bottom, and you just train a linear classifier on top of the top representation. And somewhat surprisingly, it turns out that fine-tuning more or less always does better than that, even in the few-shot learning setting, even in a setting where the amount of training examples that are available for the downstream task is actually quite small. So in this figure, you can just pay attention to fine-tuning, which is the solid line, and then the dotted line that's linear, or that's linear probe. And you can see it's essentially always below the solid line. And what's interesting is that the gap increases in terms of accuracy of both, the more different the downstream task is. And intuitively, that sort of makes sense. The more different the task is, the less appropriate might the representation provided by ImageNet training be. And this is where fine-tuning might be beneficial because it allows you to adjust the representation. And so in this work, which we call head to toe, this was led by Utku FC, we aimed at trying to have something like linear probe that is competitive with fine-tuning. And our sort of working theory was that actually fine-tuning, what it does when you fine-tune on the downstream task is that it takes some of the very informally information that's captured by early layers and figures out a way of sort of bubbling up that information to the top representation. So one thought was, well, maybe if we allow a linear probe to access the internal representation directly, maybe that's all it needs really to sort of catch up to fine-tuning. And in effect, that is sort of what we're seeing. So just to visually see this, linear probe is this. We just trained a linear classifier on top of a frozen representation. And the head to toe here is a linear probe that has access to the internal hidden units. And there are a lot of internal hidden units. So we're going to heavily regularize our linear probe. And specifically, we're going to apply some form of sparsity so that it effectively selects different internal hidden units for the downstream task. And what we find here, you have the performance of head to toe minus the performance of linear probe. And we do find that generally it actually does better. In particular, it does better on these tasks that are very different from ImageNet, either because they're sort of synthetic or the images are not so natural or the concepts are represented are quite different. And just in numbers, so you know that I'm not lying, essentially, we see numbers here evaluated on the VTAB benchmark. So this is a benchmark where people are assumed to pre-train on ImageNet, and then you have a lot of downstream tasks that are categorized based on whether they're natural, specialized, or structured. And what's interesting, you have head to toe here, and actually where it does particularly well is on these really out of distribution structured tasks that are quite different from ImageNet. And overall, on average, it does better than fine-tuning. These results were obtained by training on by using ResNet 50 backbone. And if it turns out it doesn't quite completely catch up to you, you can also do a first phase of head-to-toe pre-training of the linear head, and then actually start from that and do more fine-tuning in the full backbone if you have the resources required to have an entirely separate classifier with its own weights. We've actually found in our experiments in the paper that we kind of had to do this for VIT backbone for some reason to be able to catch up to VIT and do better. All right, but I'll stop here. I don't want to go too deeply in this, but the idea here is to say, well, when we train a backbone, maybe it's not just the top representation that's useful. Maybe there's something more in this backbone that can be extracted for solving other downstream tasks. And I'll briefly mention another piece of work that is trying to get at this, leverage this concept or this idea that's going to be presented this week from my colleagues at Université Laval, and the first author is Armen Afraziabi. And you can go check it out. But essentially, in this setting, we looked at computing a distance metric between examples in order for us to do some classification, not by comparing the distance between just the top layer, but actually allowing to do comparisons between the intermediate layers of both pre-trained or both trained backbones. And specifically, we would take the minimum. So for each layer of some query example, we look at what is the other layer in this supporting or training example that has the smallest distance, and effectively kind of pairing layers. So trying to find which representation here is closest to which representation in some training example, which allows us to sort of think more flexibly about what is the structure of the full representation as captured by the complete backbone. And we found that to be to give us a bit more better result on a few shot learning tasks. And I won't say much more about this, but you can go check it out this week. Okay, so that was one idea, to think about pre-trained backbones when we're trying to leverage them or recycle them as providing more than the top layer representation. And then the other thing that I'll discuss briefly is the idea that if we're training models all the time on a bunch of different sources, sometimes disjointly. And so how do we leverage all of that and combine that towards a downstream task? And I'll talk about two ways in which we've explored this recently. So the first work by Lu Liu, who was an intern with me and at Mila, the idea that we were trying to get at was so imagine we're in a setting where we have a lot of pre-trained backbones where we've been trained on different types of domains. Maybe one's trained on handwritten characters, another one on bird species, another one on common objects. And now we have a downstream task that's illustrated here. And we're trying to sort of think about the process of solving that downstream task as trying to first, based on the information we have about the task, fetch or retrieve the best backbone to help me solve that task. And from that, we'll just use that as the representation in order to solve the downstream task in question. And in this particular method, to represent the process of retrieving a backbone, we decided to use an attention type of process that we're now quite familiar with, which led to this name of Universal Representation Transformer. I don't want to go too quickly in the details of this, but conceptually, the query in this setup is essentially information about the task, because a query is effectively a task, and what we have to represent the task is its support or training set. And then the keys are effectively some information about each of the different pre-trained backbones that we can retrieve. And then the values is the backbone itself that we can then apply for representing the training and the test examples and do something like a form of nearest neighbor search or nearest centroid classification, like prototypical network, if you're familiar with that. And I'm not sure it's worth really going over the complete details, but the idea here was to essentially represent that as a form of self-attention, where the query would be the concatenated representation average over the full support set under each of the backbone. So again, here we're querying with a task. So we thought, well, when we were representing that task is to just look at what does the average representation look like for each of the available backbone. And then the key is simply the representation for a specific backbone that's available to me. And again, average over the support set. And so we pass that through a scale.product attention. That's going to give us attention weights on each of the possible backbone that I can use. And then to get the final representation, we essentially just do this like we do in self-attention. We just take the weighted average of each of the representation provided by each of the pre-trained backbone FI. And what's kind of nice about thinking about this in terms of an attentional network is that we can invoke the notion naturally of having multiple heads, which would mean effectively that we would try to retrieve maybe more than one backbone. So maybe one task is best represented by picking a bit of a representation of, say, ImageNet, but also of some more maybe specific data set about birds or something like that. And what we find, in fact, in the benchmark that we measured is that retrieving a single backbone was not the ideal. Retrieving two backbones was actually what led to the best results. I'm actually not going to go over the specific numbers we get. These results at this time, it's been a year, so of course they're somewhat outdated. And in fact, Hakan presented results actually better from his team, which are more recent on metadata set. But what I'll show is that these more qualitative results, which we thought were interesting, where what you're seeing here is the attention head of the model that is retrieving two different backbones. And the columns correspond to different backbones that are available, pre-trained on different sources, different domains. And then the rows are some potential source for the downstream task. In this case, we're using the common few-shot learning setting where we separated the class between classes that are available for upstream training and classes that are available for downstream training. So there's no overlap of images, but also of classes. And there's one head that has become really good at picking the backbone from the right domain, if that domain was also had also some task in the training data, in the upstream training data. But what's interesting is what the second head was doing, which is it was usually picking a complementary backbone for that task. So for instance, for a task that comes from Omniglot, if you don't know Omniglot, essentially images handwritten of different symbols from different alphabets. Well, one of the head would actually pick the right backbone also from Omniglot, trained on other classes. And then the second head would actually pick another backbone, this time trained on QuickDraw, which is also a set of images that are hand-drawn. Okay, so it kind of picked two things that were complementary, and it learned that naturally without the supervision. It learned that by just training it such that it did well on classification, few-shot classification tasks. All right, so that's one way in which we can sort of potentially have a process that combines different pre-trained backbone. The last one that I'll talk about is from this work with L3DIVU and others that we published at ICML on FLUTE. It was briefly mentioned by Hakan as the method that he beats. So I'm not going to show results here, but I think some of the concepts are interesting. So in the previous work that I talked about with the universal representation transformer, we kind of assumed that we had a collection of backbones and we can sort of pick from them. And if we don't have a lot of backbones, that's maybe useful, but that's maybe scalable. But at some point, if we imagine a community that keeps contributing different backbones, that might get to a point where there are too many. And we might want instead to have a way of compressing these backbones so that it's more manageable when it comes to solving a problem that's downstream. And so in this paper, what we were trying to explore is the idea of not have one backbone per data set, but actually have some way of sharing a bunch of parameters across the backbones of different domains while having only a number of parameters, a small number of parameters that would be domain specific. And so conceptually, the way we think about it is that each backbone is going to come from a template. The template is going to have holes, and these holes are going to be the domain specific or data set specific parameters. And the other parameters are going to be shared across backbones that they constitute the template essentially. in the experiments that we did, essentially what we were, I think, working with ResNet 50, and the convolutional layers were shared across task and domain, and then the film layers, so these parameters that are essentially a bias and scaling parameter as part of the model, would actually be domain specific. So in this setting, what we did is that we trained the template on the upstream data directly. You could imagine doing something where you actually have the backbones that are already been pre-trained on different upstream domains, and then actually doing a form of distillation. This is a bit closer to what Hakan presented, in fact, and that led to better result, but it didn't have the notion of a template here. So combining these two ideas could be interesting. But essentially, when we would train on a particular example from some domain, we would always update the same shared convolutional parameters, but we would update the specific parameters for the film layers that are specific for that domain from which the data comes from. And then when we would be faced with a downstream task, a few shot downstream task with a few examples, the only thing we would fine tune all the parameters in these film layers. So in other words, we're confronted with a new task and we're gonna fill in the slots in the template. And the template are these film layer parameters. And another way to think about this is that when we're solving a downstream task, we're kind of walking on the lower dimensional manifold of backbones for representing image data. And that's defined by the subset of parameters that we tune here, which are the film layer parameters. And at the time, that led us to get the best results on metadata set last year. But I think this is kind of an interesting concept of finding a way of taking a bunch of different backbones and potentially compressing those so that they're easier to leverage downstream by other people. Okay, I do want to leave some time for questions and discussion. So I'm going to more or less stop here. I did bring about a few sort of food for thought remarks that I think can be useful to think about more generally this notion of doing model recycling. In a way, I feel like we have some elements potentially of the puzzle, but I think it would be really interesting to think about what would be kind of a more formalized framework about engineering with deep learning model recycling. And questions we might want to sort of explicitly investigate is, for instance, what quote unquote recycling methods exist and what are their properties, in which situations do they work well. So by that, I think we can leverage, or we can sort of look at all of the different adapter methods that exist. I can mention a few of these. Residual adapters is one that works really well. Prompt tuning for more, maybe a bit more in vision, where we have a large language model, is another one where we're only tuning a subset of parameters to sort of recycle a huge pre-trained model. Diff pruning is another interesting one, where we're trying to identify only the subset of the full backbone that we're actually going to fine tune downstream, keeping all the other parameters fixed. So that's more on the sort of like, if I have some pre-trained model, what is the space of methods for recycling it into a downstream task? But then there's also the question of what are the principles that lead to models that are more recyclable for a bunch of different, hopefully a large spectrum of downstream tasks. Here, I wanted to mention one piece of work which sort of falls in a different category of forms of pre-training on upstream tasks, which is obviously quite popular these days, which is to train large language models on lots of unlabeled data, or doing a lot of self-supervised learning. And I think in a way, the reason we're really interested in that form of pre-training is that it seems to come with emergent properties that allow for a lot of different recycling towards different downstream tasks, from classification tasks, but also forms of perhaps weaker forms of reasoning. And that is very interesting, but obviously we still don't quite understand why it is that this actually emerges. I wanted to call out this particular work from DeepMind that was put on arXiv recently, because I thought it was an interesting kind of work that was trying to understand how do we actually get this kind of emergent few-shot learning behavior from transformers. And it was kind of making a point that, and this is not in the vision domain, but in the text domain, that text has this particular property where words are bursty. So when we start using a word, we tend to see it again a lot of time nearby in the same text. And in a way, that's sort of similar to how we construct episodes in meta learning, where we're going to sort of construct tasks where there's going to be a context that's going to include a concept. And then in the query set, where we are trying to, when we do few shot learning, we try to have a good prediction. We're also going to see obviously that concept, and we're going to try to learn from the context to generalize to the query. And they're kind of advocating that in natural text, that sort of is present naturally by the burstiness of property of text. And I thought it was kind of interesting. I think more work like that would be useful. Also, something that I think there's not as much work as there could be is this notion of how do we recycle a lot of models together. And I pointed to approaches that we might be able to do that. There's a lot of other ones online I'm available that people have looked at. I'm not giving a really thorough summary, but I did want to call out this one, which I thought was really interesting. And I think about these days, which is to actually find ways of combining models just by averaging them in the weight space. And it turns out there are situations where we can do that effectively. And if we could really understand in which situations we can do that and which situations we can, I think that could be really useful to facilitate the ability of people to kind of mix and matching different models and combining them, because doing averages or weighted averages in weight space is something that's very simple. And that's also in the end produces a compressed model that we sort of can build on without having the problem that, you know, our ensemble keeps getting bigger and more compute expensive. Then I was trying to sort of take even a bigger step back and think about, you know, when we think about recyclable material, there are different types of materials are recyclable in different ways. Maybe that's a nomenclature that we would benefit from defining. Maybe there are certain models that are more broadly applicable or recyclable, and maybe there are models that really should be reused in very specific setting. How do we think about that, and structuring that space would be interesting. What would be best practices to document the full life cycle of a recycled model? I think, you know, we're used to just having a pre-trained model and having a fine-tuned model, and that sort of stops there. But I think we might benefit to try to go beyond this, where we imagine a model being the result of, you know, tens or even hundreds of different combinations of different models that existed before. Well, how do we document that? Because that might be valuable to know, well, what data has each of these models seen, and what data can be truly considered as being a new example that we can measure generalization on versus not. And this also poses challenges in terms of reproducibility as well. Because if we have an artifact, a model, that's the consequence of a very complex process of combining and tuning and so on, and recycling a bunch of different models together, that starts being hard to really replicate that. And one particular line of thought that I thought was really interesting, I encourage people to look at, is this blog post from Colin Raffel, where he is trying to sort of think about what we can learn from open source software development in the context of developing these models, where we'd have notions of versions, notions of pull requests and merges and tests, which I thought he makes some interesting sort of first connections there that maybe we'd want to leverage if we want to sort of go deeper in that direction. All right, I was just hoping to present these kind of somewhat wacky ideas for you to think about. Hopefully this can fuel our discussion as part of the workshop. And with that, I'll stop here and take some questions. Thank you. Yes. Yeah.
So just first of all, what you said about software, so I think which has to do that.
Okay. What's the name of the package again? Okay, thanks.
Sure. My question is more of a business question. So after learning the whole points to kind of, you know, train a huge model, then after some, you know, the tasks. The question is, how do you convince the company to invest the engineering manpower and the cost of training the model?
Invest in training the upstream model?
Yeah.
Right, that's okay. So the question is, very practically, I guess, how do you determine whether it's worth it to invest in training these large, potentially large pre-trained model that has multiple purposes? That's a good question. I mean, hopefully you can be in a setting where there's some precedence and some evidence that for the problem setting you're interested in, that this can be beneficial. And in this case, I think you might be able to do some amount of, cost benefit analysis where it's sort of like, well, okay, so I think it would be very much grounded in the application you have in mind. How frequently will you face different downstream tasks? If you only face it once, well, maybe it's not worth to sort of think of it as first pre-training a model, a base model, and then fine-tuning it for just one purpose. But if you're gonna continuously do that, or you're gonna have a lot of, say, different customers have their own tasks or something like that, then I think you sort of can kind of lay out what are the rules of the game, what are the economics of the problem that you're trying to solve, and you can potentially try to make some small scale version of that and try to see how does that compare, hoping that these observations also apply in a larger scale. So that's sort of how I would think about it. I think in this setting, what I also like about the term recycling is that it refers explicitly to the notion of cost. Everything has a cost, and in some cases the cost is worth paying, in some cases it's not. But the only way you're going to know that is if you establish kind of what is the economy in which these models are going to be used, and what are the costs that are being faced, and so on. So I guess that's sort of how I would approach it at a high level. Sure. And also, if there's a question online, I'm happy to take one if I just look at the chat. I'll just leave it open over here. Okay, I'll answer this one in a bit. Yes.
I just had a follow-up on the previous question. When do you decide when to go back and pre-train before deciding you want to recycle the model via fine-tuning or some other strategy that you have to decide? When do you say this is not good enough and this is going to get mixed up in a local optima that will not fit my work?
Yeah, that's a great question. So I guess the question is, when do you know you're done with pre-training and then you should start doing fine-tuning on your downstream tasks? I do not have a good solution to this. Like, even if I go back, when early on in, mid 2000s, where we were doing unsupervised pre-training, we kind of treated the amount of pre-training we did as a hyperparameter, and in a very dumb way, exhaustively explored different amounts of pre-training. I think it's complicated because it might be ultimately task specific, meaning that different downstream tasks might benefit from various amounts of upstream pre-training. In a way, this might advocate for keeping around multiple models and sort of think of it as like, when I'm pre-training, I'm not generating just one model. I'm sort of generating a bunch of checkpoints. And then in terms of the downstream sort of model reuse or recycling, I'm going to think about having a process that kind of picks the right checkpoint accordingly. That's how I would sort of think about potentially approaching that. But unfortunately, I don't think there's a very, this is partly what I want to advocate for, and in some ways to kind of develop best practices for doing this, which I think if you go into different papers, you'll find different ideas that are kind of simple, but they, having them evaluated thoroughly and sort of put in the same context might be useful.
Sorry to follow up again, but I had a slightly different concept. Maybe let me count it as an example. Say you teach an AV to drive on the streets of San Francisco, then maybe we can recycle that model for the streets of New York.
Mm-hmm.
But if I want to take that same model on the streets of Mumbai, that's a completely different domain, so to speak. And so at what point do I say recycling is not good enough and I need to go all the way back to random initialization and start from scratch?
Yeah. I think if you have a particular downstream task in mind, that suggests you would want to at least have some sort of evaluation set on that downstream task. And I think ideally the way you would want to think about it is that your pre-training phase is constituted of multiple tasks, multiple training tasks. And then it's always a matter of like, which job do I take and I continue pursuing? And there's been efforts a few years ago to try to think about this and to capture this problem in a machine learning way. There's the freeze-thaw Bayesian optimization paper you'll find on, I think it's only on arXiv. This is from Ryan Adams' group. I think Kevin Swirsky is the first author, and Jasper Snook, I think, is on the paper. Where the idea is that you would represent this choice of like, which model do I sort of unfreeze and have it continue training based on an estimate of what's going to be the benefit ultimately of doing that, given how much I've trained it so far. And hopefully in this setting, you'd be able to kind of reason in a way that's grounded in statistics and machine learning for how to kind of handle that full decision-making process. That could be interesting to revisit in this setting. So that might be something worth looking at, but definitely not a problem that has a trivial solution. I have this suspicion, and I think this is another thought for me that came up when I started thinking about this area in terms of recycling. That to me kind of suggested that probably we're not frequently enough just picking a previous backbone or checkpoint and training it some more. Like maybe we should actually doing this half of the time in some ways, because in a way we're off, very oftentimes our reflexes just start from the beginning. I wouldn't be surprised if we're doing that way too often, if we really care about the downstream problem, as opposed to just starting from a checkpoint and kind of exploring a little bit around it a bit more, and maybe coming back to it more frequently than thinking about it just, doing that just one time. So anyways, I like the idea of exploring that more for sure, and maybe more formally in the freestyle Bayesian optimization paper would be one place I would start. Sure. And there was a question, how are the internal nodes selected and head to toe? So we're effectively doing a form of group lasso on all of the hidden units. And it's not all the hidden units, because even that is too many. So I think we use some form of local averaging to have fewer units that we could deal with. But essentially we did a form of group lasso. And then I think we had another formal step where we did that for a little bit, which gave us a sense of the magnitude of the weights associated with different features, where the features here are these internal nodes. And then we would just rank them by this magnitude. And that allowed us to sort of apply different amount of sparsity, which is sort of like somewhat approximately trying to solve the real sparsity optimization problem, but worked decently in our work. So hopefully that answers your question. To iPad to everyone. I'm not sure what that is, but yeah. Any other question? We're at time. Sure.
Thanks for the question, Tom. What are your thoughts on comparing this to the large language models and the stories this approach of biometric models going to be advantageous?
Yeah, sure. So I guess the question is where do these large language models fit into this notion of having, instead of a zoo of models, or one thought that came to me is first that and I think to some extent that's probably already happening, but yeah, that we should probably find ways of doing that. Like these models are really expensive to train. And so we would benefit even more from having grounded ways of reusing different checkpoints from these large models and finding ways of combining them that's beneficial and allows us to not always start from the beginning. And there's a lot of hand-holding in some ways that happens when it comes to training these models. Sometimes you do have to go back to previous checkpoints because things diverge and things like that. But there's probably something a bit more rich in terms of thinking of doing this, not just for a single training run, but multiple training runs that are in parallel. I really like this recent sort of set of papers that have been looking at averaging models together directly in weight space and trying to think about when is that likely to work, or how can we make that work? Because if it did, then I would think this is really a very effective and useful way. When we're combining different large language models are very different in architectures, that's a bit more complicated. Colin, in some way, has advocated for the fact that these models have a structure that's a little bit like a sparse mixture in sort of construction. Then you could imagine sort of combining experts together by initializing the initial gating in such a way that it does something reasonable. So that could be one sort of approach, which is to sort of introduce subparts of different networks as different elements of the same mixture of expert within a model that has these kind of components. So that could be another approach, but I think I think there's probably value in thinking more deeply about that. Sure. I guess we should wrap it up here. Yeah. All right. Thanks, everyone.